All right, I think that's the recording going there. So just before we start today, I'd like to begin by acknowledging the traditional owners of the different lands on which we all are meeting today, and I'd like to pay my respects to elders past and present. And with that, I think we're good to start, and I'll hand over to Hayley and Luin.
All right, sweet. Um, well, maybe, yeah, we'll see. Okay. Anyway, so today we are going to do a little bit of a deep dive into intakes, talking about what they are, how they work, different designs, um, and some of the theory that goes into them. So, oh, no, not going to move on. There we go. So intakes allow you to pick up game pieces from the ground rather than having to cycle back and forth between the human player station to get them. This can significantly reduce your cycle time depending on the game, as well as generally provide more options during autonomous. They can also be the same mechanism you score with, which was very common in 2018 and 2019. There are many different types of intakes for a variety of different game pieces, and we'll go over some of the more popular ones today. Okay, this didn't automatically play, but this is an intake, intaking things off of the ground. Again, it doesn't want to move on. Okay, now it wants to play. All right. So today we'll go over some of the theory concepts involved in designing an intake, look at some of the design considerations when it comes to packaging, deployment, consistency, and end on some examples of popular or cool intake designs. Some of the requirements we'll be talking about are functional and non-functional requirements, intaking from the ground, from the human player station, or not intaking at all. Touch it, own it. So wheels, claws, wide area of intake, active versus passive. Different wheel types, different packaging types, deployment types, different designs that are going to make your intake more durable, things to improve the consistency of your intake, how you can prototype your intakes, and some miscellaneous notes. Then we'll go into a bunch of different examples, which are pretty cool.
All right, so let's first talk about establishing requirements because you can't really design an intake or any mechanism for that matter without knowing what you need from it. On on day one of build season, when you first receive the rules, well, how do you go about this? First, you're going to need to figure out your game plan. So look for clever ways or just the best way of maximizing points, including ranking points scored, while keeping within your scope, which are the realistic boundaries of what your team can design and build with the resources, your people, skill sets, time, budget, etc., that you have available to you. Then, following that game plan, we need to define what your robot needs to do, not how. So you're defining essentially your acceptance criteria for your solutions without trying to overconstrain your design. So here, consider the statements, we need to get the game pieces from the ground into the goal versus we need a claw, right? Just notice that this is when you're discussing overall robot strategy. We'll go into intake specific requirements in the next few slides. This first sentence here is talking about what your robot needs to do in order to perform part of your game strategy and doesn't actually limit your design, while the second sentence goes straight into using claws without considering the other methods, which at this point in the build season, you probably haven't had sufficient time to rule out all the possibilities. Now, if you would like to learn more about strategic design, I highly recommend watching this Karthik's strategy video. He's a mentor with way too many years of experience running championship winning teams, and he does this 2-hour talk every year at Champs on this topic. So, once you've determined the what's, let's now talk about the hows. This is done via establishing your functional and non-functional requirements, which are kind of like the qualities of your robot. So, as the name suggests, functional requirements define the functionalities and features of your mechanism. This usually depends on the game and a little by the other robot decisions that you may have made so far when you're discussing your strategy. When you're designing intakes and deciding what it needs to do, the main considerations are one, game pieces. So what are their physical properties? How many do you need to worry about at any given time? You need to be designing a mechanism that can obviously control and intake the game piece. And you need to be taking into account the shape, size, weight, etc. You also need to be considering how many you need to control at any given time. How many can you hold? Do you expect to need to intake multiple at the same time? That one feels like a pretty obvious uh, functionality, right? The game piece. The second consideration that you need to look at is the location that you're expecting your game pieces to be in. Once you've figured out your strategy from earlier, you probably also know where you want to be getting your game pieces from. For example, the feeder station or maybe an auto where the game pieces are located, whether it's from the floor or from an existing game structure. But when you're looking at intaking from the ground, you also need to think about, is it going to be an open field or are you going to be intaking right up against a wall, maybe even in a corner, right? Your intake design is going to change a little depending on what you want to be capable of. And then the last consideration is, what are you going to do with the game piece afterwards? For example, you might need to serialize it to feed into another mechanism. Or maybe you need to just pop it into a hopper to hold the game pieces until you need them. Or perhaps you just want to hold it in the same mechanism and just straight up outtake it to either shoot it or place it and score it. You also need to think about if there are multiple locations that you need to score in, and if your intake needs to be designed to be able to handle that via outtaking. The next thing we're going to look at are non-functional requirements, which are the properties and attributes of your system or its qualities. These are three of the most important qualities when it comes to intakes. One is durability. The reason for that is that intakes are often out of your frame perimeter, so it is going to be coming into contact and colliding with other robots and the field in general. You also need to have a consistent intake. Intakes are interacting with external things that haven't yet been processed by your robot. And what I mean by that is that the game pieces, your robot doesn't initially have control over them. So you need to consider handling them in different orientations, different positions. It also needs to operate many times in a match. In some years, you literally need to intake hundreds of game pieces. 2017. You also need to control the game piece to go in the same spot and same orientation every time for the next mechanism or action that you're going to be doing. And then the last quality that's really important is how fast your intake is. And we're going to look into this concept of touch it, own it. Because of the high-speed nature of FRC, now with Swerve more than ever, your intakes are going to need to be able to pick up game pieces on the fly. And so I'll go into the theory on how fast your intake actually needs to be a little later. So there are, of course, other qualities that make your intake that are good for your intake. And depending on your strategy, perhaps those qualities are also going to make it on the list. These are just generally the most important ones that shouldn't be compromised. For example, you might want a really light intake and therefore lighter robot, less weight to pivot and all of that. But depending on your financial resources or machining capabilities, that might not be the most valuable use of your time, especially at the risk of making your intake less durable, right? Alrighty. So before we dive into the specifics of intake design, we'll just quickly talk about whether you need an intake at all. And a few slides ago, we talked about needing to establish a game plan, right? The strategy that your robot is going to be designed for. One of the things that you need to identify is what you'll be scoring and where you can get the game piece to score. Usually, every season, you can access the game piece from the ground. And these are the intakes that we'll be focusing on today. But they're not the only ones. Human player stations. are locations on the field where you can load your robots in a relatively controlled manner, and also something that I'm pretty sure you see yearly. Just note that this can also work with ground intakes. If you just drop the game piece on the ground, usually your ground intakes should be able to handle it. There are some exceptions to loading from the human player stations. So for example, I think 2016, the human players essentially had to bowl down a lane for the robot to then pick up from the ground. So there was no option for you to load it in from the top. Next are field structures. So for some game pieces, most teams choose to get them from field structures. For example, 2017, where there were just many balls that you would crash into a wall and they would all just fall into your robot, or 2018, where they started at the top of this truss. But then in the case of 2010, one team will choose to get their game pieces from the field structure. Only one team will choose to get their game pieces from the field structures. And this is a very clever robot that really didn't build an intake. So see how the ball is falling from the ramp at the top into their robot, which was essentially just a ramp, and they scored it that way. So that's all well and good, but one year, one team decided to just build the fastest robot possible and not bother with interacting with the game pieces. 148 in 2008 decided to just drive around the field for the entire match, which was actually one of the ways that you could score. Yeah, and there it goes. So the point of talking about all this is just make sure you understand your game plan before jumping into designing an intake. They are a very common mechanism that you will see almost every single year, but they are not always needed, depending on your strategy. Now, let's talk about intakes. So, the first concept we're going to talk about is this concept of touch it, own it, which essentially is one of the most important intake design rules. You want to be able to drive at the game piece and end up with it in your robot or in your control. This means that as soon as your robot contacts it, it owns it and cannot be stolen by another robot or cannot be lost to collisions or anything. We're going to explore 4 different ways that you can achieve this. One, we're going to look at having as wide of an intake area as possible, ideally the whole width of the robot. We're also going to look at the ideal speed of your intake, which is that the wheel surface speed needs to be greater than or equal to 2 times your drive speed. We're going to look at active control of your game pieces from the first moment of contact, and we're going to look at using wheels and rollers to maximize your contact and grippiness. All right, this first point, we're going to, well, when you design an intake, you want your intake to have as wide of an intake area as possible so that your drivers don't need to waste time and mental bandwidth on lining up to the game piece. On the right here, notice how we have 2 different designs. That first one is a top roller design, whereas the second one has the wheels on the sides. Notice how it's much harder to get a wide area of intake with your side roller intakes. But it's still possible. So in this example, this is sprung with surgical tubing to widen the outer intake wheels when it's in contact with the game piece. In which case, this case, it was a milk crate. Yeah, so Luin there is pointing out where the surgical tubing is. But yeah.
Surgical tubing is sprung from here all the way back to the frame. And so as these wheels make contact with the game pieces, they ride up the game piece and open to the width of the cube that year.
Yep, exactly. But yeah, the whole idea of this is that you should be able to drive at the game piece's general direction, and be able to have it in your robot. The one problem with full width intakes is that you are going to need to, most likely, need to center the game piece or index it in some way. And having the robot having the intake be the width of a single game piece means that you require more driving accuracy, but you don't need to index. So that's a thing to think about, but we'll look at some ways to index your game pieces in a moment. The next thing that we're going to talk about is this rule that gets quoted way too often, for good reasons, which is that your intake surface speed needs to be 2 times your robot's drive speed, at least. This applies to intakes with a top roller to ensure that at all points in time, even when you're driving forwards at your top speed, your intake can still operate. When you drive into a game piece, you want to make sure that the game piece is rolled towards and into our robot instead of our robot rolling over the ball. Yeah, so there's a graphic on the side to kind of show you what's going on. That top bit is showing where your surface speed is greater than or equal to 2 times your drive speed, which means that the intake roller is going to be spinning faster than your ball no matter what. And that bottom graphic there is showing when your intake is less than 2 times your drive speed. When you're traveling, what's mouse say? Okay, sorry. When you're traveling at your max speed, there's a chance that, well, the ball. So if the ball at the point of contact with the field, isn't moving at all, the speed of your intake is going to make it so that the top of the ball is God, where's the mouse cursor?
I don't know what the mouse cursor looks like, so I can't help you.
Actually, do you want to explain this just because you
Yeah.
have the mouse? It's probably
Yeah.
a little easier.
So this pink triangle is basically the contact point between the ball and the ground. So when your wheel is over double your drive speed, so that's the linear speed of your robot, your wheel will pull the ball in towards your robot. So the intake wheel spins, contacts the game piece, and then the game piece will get pulled into your robot even as your robot is moving forwards. Whereas when it is under twice your drive speed, your wheel pulls in the ball still, but it's slower than you're moving. And so the ball actually gets pushed away from the point of contact with the ground before it goes into your robot. So that can cause some issues where if you have a robot that has ground clearance that's kind of close to the game piece, you will be driving forwards and then you'll hit that game piece, and instead of the game piece pulling up and into your robot goes up and over the game piece and tips, and that's no fun for anyone.
Alrighty. Let's look at the next thing, which is this idea of active versus passive control. And what I mean by that is that ideally the game piece should always be in contact with parts of your mechanism that have control over it. You don't want to be relying on gravity if avoidable, and you also don't want any dead spots in your intake for the game piece to be jammed in. Let's take a look at this video, and it should show you exactly why. Intake's working great, but the balls are going a little bit all over the place. Obviously, this is just a prototype. I don't expect the Ed robot to be like this, but it does show why we need this active control over the game pieces. Because yeah, we really don't want to be designing a perfect intake and then losing your game pieces all over the place. Alrighty. And I think this is the last point out of the 4. Yeah, compliance and compression. So along the same lines as this active control thing, the last point to consider when you're designing a touch-it-own intake is how you maximize your contact and grip on the game piece. For intakes to be actually controlling the game pieces, they need to be in contact at all times to be imparting energy. And to do that, you need to understand compliance, which is the ability of a mechanism to flex and adapt to external forces. And in this case, it refers to molding the intake to the game piece or molding the game piece to the intake, such that both are in constant contact regardless of their shape, even if the game piece is a slightly different size than the others or slightly damaged, or even during high acceleration changes, such as in collisions. This also results in a design that's really forgiving of variations in alignment. Typically, for hard game pieces, like the 2018 milk crates, you want to be using compliant wheels and or add compliance into your mechanism so that you maintain contact. For the softer game pieces, that's when teams can start looking into farther wheels or just a singular top roller to compress the game piece instead of the wheels. Let's look at some examples of designing compliance into your intakes, and then we'll take a look at the wheel and roller options that are commonly available. So, one way to achieve compliance in your designs is by making your intake springy. This can be done using surgical tubing to allow the location of the intake wheels to dynamically change depending on the orientation or the location of your game piece while you're still maintaining grip on it. Here's 148's intake from 2018 as an example, where they can intake from any orientation because of the springy nature of the intake, even if it's slightly on a diagonal.
So you can see here that their intake deploys out. Oh man, that's right. I was going to open these in. So you can see that when their intake, their elevator goes up a little bit, their intake is basically unlocked. And so then their arms swing around using that surgical tubing. And then you can see right there, they bounce back. And so that's the springiness in the intake. And that carries over for when they're intaking the game piece as well. They come in and that intake gets wider around the game piece until it's in its possession. You can see here again, the intake actually can't be seen at all, and then it pushes its way out around the sides to then suck that cube all the way in, making sure that it owns it and it's not going anywhere. Again, you can see that when it does the opposite and puts out the cube, those intake arms spring back in, back to their original position. Oh, okay, cool. Oh, no speaker notes.
Not allowed? Yes. You're good?
Okay.
All right, so this next slide here is just the same concept, but just showing you that this concept applies to intakes with a top roller as well as the side rollers.
Oh, okay, well. So you can see as the robot is driving over the game pieces, it is complying with them and it is lifting the intake up, bouncing a little bit, which probably isn't ideal, but it does get the job done. I'm locked in here. Okay. There we go. I guess we'll watch it one more time.
Thanks, Google Slides. All right. So this next example here is 118 from 2018, where they are using pneumatics to achieve the same results, where instead of the surgical tubing, it's compressing air that's providing the springiness.
So you can see at the back here in this image, you have, well, there's like 5 pneumatic pistons back here, but these ones and these ones don't actually matter. There's one back here that when that actuates, pushes these arms in and out relative at the front, and then you can see as the game piece is being picked up. Wait, can I do this? And then as the game piece is being picked up, you can see the exact same behavior as the surgical tubing sprung one from 148. The wheels pop out and back in until it has that game piece right where it needs it and has full control over it. You can see again here as it comes in. You can even see the pneumatic piston here in the corner. It's able to spring in and out. And this is because air is still compressible. So it can act like a spring. Oh, okay, no, cool. I thought I played it from the beginning.
Alrighty.
Okay.
So once you've found a way for your intake to be contacting the game piece at all times, you need to figure out what materials to actually use. Wheels are the go-to solution for many, many teams, with compliant wheels being the top choice because of their availability and versatility. The surface deforms upon contact, which provides the compliance that we're looking for to maintain control of your game pieces. The durometer number that you see here are the 35 to 60A numbers that are written there. Just measures how hard the wheels are, where green is the most compliant and black is the least. And if you want smaller wheels, Andy Mark sells these sushi roller wheels designed for compact intakes. When you put many of these in a row, you end up with just a roller, which we'll look at in the next slides. Sometimes you'll also see other wheels, like Colson's for softer game pieces, pneumatic wheels back in the days for 2015. But these are the most common and effective options. So lots of teams don't use wheels for most of their intakes and instead are going to use rollers, which also can have something wrapped around it to increase the grip. This makes for a much more compact intake and lets you have the same breach along the entire width. Whereas using wheels, they are likely spaced out or you're just going to have a really heavy intake. But them being spaced out does mean that some sections are going to have more reach than others, which may or may not be what you're looking for, depending on the game piece. Rollers are usually made from a polycarb tube, if you see any of the teams from the US. But here in Australia, PVC pipe tends to be more commonly used just because polycarb tubes are really, really expensive here. I think, Luin, you were looking into some last time and it was what, 200 for how much?
400 for 3 meters of 2-inch.
Yeah.
It was not good.
Just a little bit too much. I think
Whereas for the
Bookmaster was
Americans,
what,
yeah, for the
a
Americans,
quarter of the
Bookmaster
price?
car's like $100 for 6 meters or something. It's nuts.
Yeah. Anyway, unless the game piece itself is really grippy, like the 2020 game pieces, you are usually going to look to coat these tubes to get more grip onto the game pieces. Most commonly, teams will use silicone tubing, which is floated over the tube to give better grip. But in 2022, Velcro and cat tongue tape were the most common coating materials. Where the game piece were oversized tennis balls, and the surface was essentially the hook side of the Velcro. So there are also two main ways to make rollers, either with a live axle or dead axle. Live axles are where the axle itself is spinning and the roller is connected to it, whereas the dead axles have the roller spinning and the axle remains still. The live axles are the most common because they are just easier to design and manufacture, but they are also going to be heavier and more prone to damage because the axle can get bent. Dead axles are usually made with a really short stub axle on each side of the intake. One's pointing it out there. and the roller is constrained to each end with a tube plug. Yep, right there in the image. That's an example from 254.
So this is most common in the US with the polycarbonate tubing. So these parts here are bearings. Then you have your bolt holding it to the side of the plate. And then this outside part is a 3D printed part with a pulley built into it. So your pulley is attached to your tube. And so as it spins, the tube spins around the bearings that are on the tube plug here. This is very common with the polycarbonate tubing rollers, but I don't think that this should be done with PVC pipe because it can fail quite brittly, and be quite sharp if you run into things and break it.
All right.
We do have a question relating to rollers before you move on. Luke is asking, what do you think of using like tape wrapped around rollers like PVC pipe to increase grip?
It depends on the game piece. I think this year we used PVC pipe with no coating and it worked pretty okay. Previously we've used Velcro, like in 2022. I know teams this year did use some tape wrapped around theirs. I've seen heat shrink being used, but PVC pipe itself tends to be a bit more grippy than the polycarbonate tubing. But for most game pieces, you will want to coat it with something if you can.
I will also say that it does come down to testing at the end of the day. You do want to just test out a bunch of different options and see what works for you guys.
Yeah. Yeah, grip tape. Grip tape is very common as well.
Okay. Another common part that you find in intake design is a vectored wheel, which are a special type of wheels with passive rollers at 45 degrees around their circumference. And the video should show it, but it'll pull in the game piece towards your robot, and then when it can no longer move in that direction, you'll see that it's pushed in the direction of the rollers. And you can orient them so that they center the balls for you, or push them all to one side, depending on where they need to go next.
So these ones are quite cool. You can actually 3D print them yourself as one part. So these are all print in place rollers, which are pretty cool. We used them in 2022 to center our cargo. And yeah, they work really, really well.
Sometimes you're going to come across game pieces that are irregularly shaped. You might be tempted to consider claws for them, but remember, you do want to have control over the game pieces as quickly as possible, and it's far easier to do that with wheels and rollers than to try to line up with a claw. And one last thing to try and convince you that wheels are the way. Wheels can do some really cool things. When it came to 2018 with the milk crates, most teams built intakes with compliant wheels to grip onto either side of the crates. Some teams chose claws, and some teams used wheels to pick up the crates by pinching an edge of the crate by its fabric, like this one. This unconventional style of intake allowed them to have a much lighter mechanism than the other teams, which was especially important because you needed to lift these game pieces up very high that year. And so having lighter moving parts just makes your robot so much more efficient.
So now that we've learned about how to control the game pieces, how do we package these mechanisms? So packaging is the art of fitting all of your mechanisms together within your robot's size constraints. And there are many things that you need to think about when making the decision about where you want them to go. Some of the factors that you must think about are safety and durability considerations. So can your intake be protected from collisions? The size of the game piece, can it go underneath your bumper? Where does the game piece go afterwards? Does it go into a hopper, or do you hold it in the intake and score it straight away? And where does the intake start and end? Does another part of your robot actually get in the way of that motion? So keeping these in mind, we'll look at the two primary options for intake archetypes, the cutout or under the bumper and over the bumper intakes. So the cutout archetype involved using a cutout in the robot's bumpers and frame to intake game pieces through, meaning that the intake can sit within the robot's frame perimeter, not requiring any deployment to be able to intake game pieces. This design was quite commonly used in seasons prior to pre-2024. However, with the introduction of the maximum bumper gap of 1/2 inch for that year, and the continuation of this rule with the maximum bumper gap now being 1.5 inches for 2025, the cutout archetype of the intake has been made illegal, and I suspect that it will stay that way given the speed of robots in the modern era. With the loss of the cutout, though, it was thought that for the 2024 season, the only way to intake game pieces would be to intake it over the bumper. But due to the 2024 game piece being only 2 inches tall, it was viable to intake them from under the bumper, protecting the intake from collisions, similar to how the cutout would have. But this time, there was no cutout for the corner of a robot or field element to reach through and cause damage. So if you were to drive this robot into the field truss, you could very much bend this bar and you would have the field truss be breaching your frame perimeter. However, because there's no cutout in the bumpers, that can't happen. This was beneficial for two main reasons. The lack of need for a deployment mechanism makes this design compact and extremely simple with fewer moving parts. It also means that the intake's generally well protected from collisions with another robot or a wall, as the bumpers at either side of the cutout make contact before anything within the frame perimeter does. However, as I said, it's not foolproof, because it can be damaged by the corner of another robot or a field element reaching past the bumpers and damaging your intake. As with most things, though, there are some downsides. You're very limited in your intake width, as for the cutout at least, you had to have 6 inches of bumper on either side, and you have shorter reach than other robots, meaning that it was hard to intake from corners of the field, or if, like in 2024, you're racing with another robot to get to that center line, you lost a lot of reach because you had your intake behind your bumpers. So note that for under the bumper intakes, the lack of a cutout meant that they were actually fully protected against corners, and you could have a full width intake. However, it either increased the design complexity or it took out a large amount of space in front of your chassis. So to negate the downsides of cutout or under the bumper intakes, you can deploy your intake over your bumpers. These are aptly named over the bumper or OTB style intakes. This makes your intake more complicated and less compact, as you must have a mechanism that deploys the intake, and it must be durable enough to survive impacts with field walls or elements and other robots. But you're now free of the width constraints of the bumper gap, and you gain extra reach equal to that season's extension limits. Generally, that's 12 inches. So, because over-the-bumper intakes must be deployed, as the name suggests, over the bumpers, you'll need to design a mechanism capable of achieving this. Typically, your intake will have two positions. Position 1 will be stowed within your frame perimeter, so that you can actually start the match legally, and position 2 will be deployed, ready to intake a game piece. There are three main types of intake deployment mechanisms that we'll discuss: sliding out, slapping down, and the forebar. We'll also go over the three primary methods used to deploy them, using passively deploying them with gravity, springs, and surgical tubing, actively with pneumatics, or actively using motors. Each of these deployment mechanisms and methods have their pros and cons, which we'll discuss over the coming slides. So slide-out intakes are probably the least common deployment designs used in FRC, because they're really only explored when you require the vertical space in your robot for the rest of your mechanisms. This is likely due to the way they package, as early on in the season, when you're planning out your design, you block out space for each mechanism, and by blocking out a horizontal slice for the intake, it makes it harder to conceptualize how the rest of the robot goes together and how the mechanisms integrate with each other. The primary downsides of a slide-out intake are that they can take longer to deploy, as they generally have to cover more ground than a typical intake does, and they can take up a large amount of space across the robot. So you have here 148 in 2019. The entire side, like few inches of their robot, are taken up by this slide in-out mechanism. And same with this little mini bot from Lynx in 2023. They are shooting a 2022 cargo ball, but this is a 2023 off-season robot that was designed to shoot the little inflatable cubes. So to avoid the downsides, most teams choose one of the two pivoting intake options, as they're generally easier to design and package anyway. So the first pivoting intake deployment design we'll look at is the slap-down intake. The slap-down intake is the simplest of the deployment methods, as it involves the intake rotating around a single pivot point. The location of this pivot point can be almost anywhere on your robot, so you can pick the geometry that works best for you. Slap-down intakes are generally also the lightest and easiest to package, making them the most common intake type seen in FRC. The main downsides of the slap-down intake is that sometimes the area of the robot that the intake would pivot up into is occupied by other mechanisms. So if we have a look at 4414 here, you'll see that their intake drops down, drops down slowly using, well, not slowly in this case, but they use a motor to pivot their intake around this point here. And during a match, it's very, very quick and it slaps down very, very fast. They have this polycarbonate hard stop here as well to make sure that it stays at the correct height whilst it's being used. And over on the left here, we have 254's 2016 robot. They have a pneumatic piston on either side that pulls back at this point. The intake pivots around here, and so as this gets pulled back, the whole intake here lifts up, and so it stows vertically in front of the robot. But as I mentioned, sometimes you'll have something in this area that you don't want to have this intake all the way up in. You'll need something that's a little bit more low profile. So we'll use a 4-bar intake. So a 4-bar intake consists of 4 bars, as the name suggests. You have 1, which is your chassis, 2, which is the front actual intake, and then you have 3 and 4, which are the arms here. They can both be powered by pneumatics in this case. So this is Cybertooth. They had their pneumatic piston here. When it's pushed out, the intake is deployed, and then when it pulls in, this whole section retracts into their robot. Here we have a video of 6328, their prototype in 2020. So there's a couple of different things you can do with a 4-bar. You can design it so that where it is stowed, it is on the same angle throughout the entire travel. So that's a parallel 4-bar. But then you can also design it so that your start position and your end position have 2 different orientations. And so this is really, really useful for when you have limited space. Say this mechanism actually extended out a little bit, and you wanted this to be stowed back here, but still deployed in this angle. You can change the lengths of these linkages and the angles of the linkages, and you'll be able to have different geometries. There's quite a few resources out there on how to design 4-bars. The way I've done it in the past is just trial and error in CAD. Probably not the best method. I'll link a video in the chat right now that has, I stumbled across researching this, that helps with how to design a 4-bar. So, as I said, one of the things you can do is just test and trial and error. One of the ways you can do that is by using adjustable plates when you're prototyping, but we'll talk about that a little bit later. So we'll move on to the first deployment method, which is passive. So a passive deployment relies on either a jolt of your robot at the start of the match or movement of some kind of mechanism to dislodge the intake. And then once it's deployed, it will stay outside the frame perimeter the entire match. This leaves it susceptible to damage, so probably isn't the best. But if you're running low on motor count or you don't want to use pneumatics for whatever reason, then this is one way to do it. So these guys will, I'll open this up. This will be easier.
Are you sharing sound? I think they talk about it in this clip as well.
I am not sharing sound. I forgot to tick that box. But
All right, all good.
you can see here they have a gas strut, which is basically a pneumatic piston that isn't connected to your pneumatic system. It has compressed air in here that always wants to push out and basically acts as a spring. Then they also have this surgical tubing that again acts like another spring. So as their indexer hopper thing here spins around, it unhooks the intake. And then because they have a spring here and a spring here, it pushes the intake out and deploys it just passively without any pneumatics or motors driving this in and out. So they're just using the pre-existing motor that they have for the hopper to deploy their intake at the start of the match. It then stays out the entire time, which they have designed for by having it be made out of polycarbonate and really thin, lightweight, and robust, which will go more into durability a bit later. Oh my God, why does it do this every time? I'm just going to start the video and then I have to skip through. Yeah, okay. So, as mentioned previously, the intakes can usually be viewed as a two-position system. One position is stowed and the second is deployed, ready to intake. This perfectly suits the applications of pneumatic cylinders as they have two states, extended and retracted. This makes design relatively simple, but designing around the pistons you have is a bit of a challenge sometimes. Keep in mind that if you have a pneumatically actuated intake, you'll require a large number of air tanks because you'll be deploying and retracting it many, many times within a match. Also, pneumatics are very, very susceptible to damage. So if you have your piston sticking outside your frame perimeter and it gets hit and bent, you will very likely not be able to use that anymore. Because even if you bend it back, you'll generally have some misalignment and it will get stuck trying to pull in or out, or the seal will be broken and you'll have air leaking through to the other side. So on this side, we have a pneumatic 4-bar, which 5985 designed in 2022. You can see we have, can I loop this? I can. We have some pneumatic pistons here and one here that connect to the top bar of the 4-bar here. Then the bottom bar is here. And so as the intake is pulled back in, whoa, there's a slider? Okay. As the intake comes back in, this bar is being pulled back and the rest follow. So in this case, this was not a parallel 4-bar. When the intake is out, we have a steeper angle than when it's retracted. And this was so that we could have the correct angle that we found during prototyping, but we were able to fit it within our frame perimeter when it was stowed. As you can see, these are PVC pipe live axles that are coated in Velcro tape. Second over here is a pneumatic slapdown intake from 2910 Jack in the Butt. We can see, and this doesn't have a slider. What on earth is going on? As their
Google Drive
piston
versus YouTube.
I guess so, yeah. Actuate, there we go. So as their piston actuates, their intake bar pivots around a point down here, which brings it down, ready to intake a game piece. Now, if we run this back. So you can see they're using the vectored intake wheels, which suck it in, and when it goes up against the bumper, it pulls it across and in. You can again see that they have a bumper cutout. This means that they don't have to pull the ball up as high, and so it can have a lower profile robot. But as I mentioned before, the bumper cutout is a little bit dead now. And you can see that when it comes back in, it pivots up again around the same point. Oh, there's the intake and up. Pivots around here, bring it up and back within the frame perimeter. So, okay, now there we go. So, although pneumatics is great for being two position, sometimes you are only going to use your pneumatics for your intake and nothing else. Then you'll need to take into account how heavy a pneumatic system is. You've got your compressor, you've got your air tanks, you've got your cylinders, and all the associated tubes and fittings, and it can get quite heavy. And so if you're only using it for your intake, it's not really worth having it on there. So the method that is becoming more and more common is the using a motor to pivot it. So this 4-bar is being pivoted by a motor. That's this axle here. No, yeah, this axle here, the motor's down here, and the chain connects the two. So as the motor spins, it rotates the chain, which pulls this axle along, and just like how the piston pushed the top bar of the 4-bar, this axle drives that top bar. And so this is now becoming the most common method. I believe that the switch started happening towards motor power to drive intakes when they mandated that the compressor had to be on the robot. Previously, you could have an offboard compressor and a whole bunch of tanks that could just power your pneumatic cylinders, but now you must have the compressor on there, which adds, what is it, like 2 or 3 pounds? It's a very heavy chunk of metal. So yeah, using motors means that you don't need pneumatics. So if you don't already have pneumatics on your robot, it means you don't have to add them. And it also allows for rapid and precise positioning for your intake. It also means that if you do want to have multiple positions, so for this year, if you wanted to have an intake that picked up off the ground, was able to stow within your frame perimeter, and then also poke out to score in the amp, you could do that. In this example, the intake is being pivoted by a chain and sprocket system in the center of it, but it can also be done over to the side. I guess we'll watch it again. So another way to deploy an intake using a motor is a winch. This is not really that recommended because it can be slow and tangled and relies on gravity. But you can see up here we have a winch with a cable that pulls the intake up and then releases it down. Very, very simple, but again, not really recommended.
All right, so going back to our discussion about requirements from earlier, the first non-functional requirement that we had prioritized was durability. Why? Well, for an intake, it's guaranteed to take hits, so it needs to be designed with that in mind. Consider it as, I guess, the second most important part of the robot after the drivetrain, because if you can't pick up a game piece, then there's really not much you can do in terms of scoring it. If your design is sticking outside of your frame perimeter, it needs to be designed with robustness and also serviceability in mind. Looking at materials, more for over-the-bumper intakes, the material that you make your intake from matters a lot. I saw Mel typing in chat earlier talking about polycarb. That's that's exactly what you want to be using for your intake. Essentially, you want to make your intake as durable as possible, but you do also need to decide if you want to make it compliant or rigid. Compliance means when it gets hit, it's going to bend and flex back into its original shape, which polycarb is really good at doing. And generally, we'll be using the 6mm polycarb sheets. Rigid means that when it gets hit, it doesn't move at all. Some teams choose to go down this path and make their intake from thick aluminium plates and tubing with thick walls, which makes it highly resistant to bending, but it also means that if it does end up hitting something and bending the intake, it's going to stay bent. It is going to permanently deform, which then could potentially result in you no longer being able to use that intake and needing to bring spares. Yeah. Let's go to the next slide.
Maybe if it wants to. Okay, there we
Okay.
go.
There we go. So, similar to the last video, you want to be testing multiple times. You want to be testing your design before comp. Stress test it. If it breaks, it probably was going to break during the chaos comp anyway, and you're going to know from this testing what to redesign or bring spares off.
Why does it take like 3 presses to make it change a slide?
When designing, you're also going to need to keep in mind where and when impacts are going to happen, and also use that to figure out what important or expensive components you're going to need to protect. Using pneumatics as an example, we talked about using pneumatics to pivot your intake, right? If you can, you want to try and design your pneumatics so that they're closed when your intake is extended. And this is because your intake is going to be taking impact when it's extended, and you want to be protecting your pistons. And your pistons are most vulnerable when they are extended. So, if you design them so they're closed, when the intake is extended, you make it so they're more likely to be able to continue operating smoothly.
So
And
yeah, in
then,
this example here, we have our piston that is retracted when the intake is out, and then when this piston extends, this is the top bar of the 4-bar linkage. You've got one here and one here. As this goes up, this whole system pivots in to be within the frame perimeter. And so by putting the piston in front of this bar instead of behind it, like in the 5985 example, we're able to have it be retracted instead of extended whilst deployed. And as Hayley said, protecting it fully from being bent.
We have another question in the chat that you might want to answer. Another question from Luke, which is, what do you think about composite materials like 3mm polycarbonate in 2 pieces of 1mm aluminium, so sandwich structure?
It generally, so when you're building an intake, you want to either build it so that it is strong or so that it flexes. By sandwiching the polycarbonate in the aluminium, you are taking the worst part of both of them. Well, yeah. So your polycarbonate will bend, but your aluminium sheeting will also bend. And then your aluminium sheeting then stops the polycarbonate from being able to flex back into position. And so you'll have a permanently deformed intake instead of having one that will bounce back. And then because the aluminium sheeting is so thin, it doesn't give you the rigidity that you would have out of like 6mm aluminium plate. So I believe we have a bunch of that composite, is it Euroboard or something? We got it from a guy who was giving away a whole bunch of sign making material. We used it on a prototype intake one season, and then it sat in our storeroom for years now. We haven't touched the stuff again. I don't know what the plastic was, but it was also very, very brittle. And so if you don't know exactly what it is, then you probably best to avoid it. Does that answer your question? Cool.
cool. And then the other thing in the comments, I should have said at least 6mm. Teams in the US generally tend to use 1/4 inch, which is what we were going off there, but thicker, it does tend to be better.
Yeah.
It depends on what kind of impacts you're likely to be seeing.
I don't think I've seen anyone in Australia use 12mm polycarb except for Iona Fusion, who built their entire robot out of it for quite a few years. It was very, very cool.
I think if you're buying it here, you're more likely to get 10mm as the main option. And also, if you've ever recycled field components, they used to make some field components out of 3/8 inch, which is pretty close to 10mm.
9.58 or something.
Yeah, something like that.
Yeah, at least 6. Don't go overboard. You don't want to design a really, really heavy intake that you're going to have to pivot in and out multiple times. Yeah. Anyway,
No, Noah.
let's talk about assembly, which is the last point that I had here for durable designs. Well, seeing a bearing pop out of your intake might just be one of the worst feelings. And it happens so often with polycarb intake plates because they're flexing so much and the distance between them can so easily change. Luckily, this is pretty easily avoidable. And here we have 3 common solutions for securing the bearing. You're going to want to be securing it via the flange, or like the outer part of your bearing, just because the inner part is going to be spinning and you don't want to be rubbing on it. So you can either have a bearing mounting plate that they're bolting to their intake plate there. You can have your bolts with washers, or in the case of this image, one large printed washer. And then the last option you have are rivets. You can just rivet the uh, outer part of the bearing, outer race of the bearing to your design. The other thing that we were talking about when it came to the uh, requirements from earlier was consistency. So this means that your intake needs to be performing in the same way every time. With an over-the-bumper intake, you want to be in the match, deploying the intake to pick up a game piece and then retract it back into the robot to keep it out of the harm's way. And you can actually do that with sensors and also in conjunction with hard stops to prevent the intake from destroying itself when it's doing that, right? So you can use sensors to see when your game piece is coming into the robot. And then once you know that you have your game piece in a place that you can control it, you can then bring your intake back up into your robot. And that's a process that can be done automatically without your drivers needing to think about it. The sensors that you're most commonly going to be looking at are beam breaks or color sensors, which will detect when you have picked up a game piece. You're also going to need to consider how many game pieces you can hold at a time. Some years you can only hold one at a time, other years you might only be able to hold a couple of them. And by having sensors, you can have them count the number of game pieces that are coming into your robot and tell your intake to stop or start outtaking if you've accidentally picked up more.
So, as we briefly mentioned earlier, prototyping is a great way to be able to figure out your compression, your correct heights, distances between rollers, size of rollers, which type of intake to use, all of that sort of stuff. So on the left here, we have a model of an adjustable intake prototype where you're able to undo or loosen off these screws and then slide the intake arms around relative to each other all over the place and tighten them back up. And then that way you're able to test a whole bunch of different configurations. I will put the link to this Chief Delphi thread in the chat. It has that model and you can download on Onshape as well. Very, very cool. And then over on the side here, we have intake plates done by Rembrandt's, so team 4481. You can see they have slots for, or all these holes are bolt holes, and then their roller is going through 2 bearing plates that they've 3D printed. And then this slot is the perfect size for that plate, and they can put that along anywhere along here. Then they have another roller, a position for another roller at the top, and another one here. And so they can have up to 3 rollers on this. Here they're testing with just one roller, and then here they use the exact same plate, but add another roller up here connected with a belt. And then you can still see that they have a third spot for a third roller if they need to use it. So for prototyping, being able to quickly on the fly adjust all of these things is pretty key to being able to do it quickly.
And then also adjusting them in a way that you can come back to them next time and record what you've done. I see
Yes.
too many teams just clamping their testing down and then not knowing how to exactly replicate it again next time.
Another way to make it adjustable is by using these 3D printed clamping blocks. So you can see here that these 3D printed blocks have bearing holes, and then you can undo these to loosen off the clamping and then slide them all around. This is Spectrum, and so yeah, they could loosen these off and slide it that way if they thought they had too much compression, or if they don't think they had enough, they could slide it in closer. This whole prototype here is another example of using rollers or wheels instead of a claw. Even for a funky game piece, try and exhaust all of your options to see if you can use wheels or something to pick it up. And next we have intake outtake. So for most intakes, you will just be intaking the game piece, putting it into your robot, and then it then goes into a hopper or some sort of area to wait to then be scored using a shooter, or it's handed off into another claw or something to then be scored using a different mechanism. But what you can do, like 118 did in 2019, is have it be both. So this was their intake. They had it to intake a ball, and then they held the ball in here and went and scored it just by spinning these in the opposite direction. So they were able to use the exact same mechanism for both intaking and scoring. So before we take a look at some of the example intakes, we'll quickly discuss why we're going to look at example intakes. So one of 1678's golden rules is steal from the best, invent the rest. And I think we should probably listen to 1678 and their golden rules. They currently have a 10-year streak on Einstein, and so they've clearly figured out what makes a winning robot. This piece of advice isn't specific to intakes either. It really does show the importance of doing your research on existing work and using your time in the most efficient way. It all basically comes back to the phrase, don't try to reinvent the wheel. There are currently existing solutions out there that work extremely well. It's all just about finding what's already out there and building upon that. So this first example is from Team 125, the Neutrons, for the 2017 game. So you can see they had a passively deployed intake. It is currently, there's this bar here, and then as they move that bar down, the gas struts here and here push their intake out. So this is now stuck outside of their frame perimeter, and so must be able to take impacts from other robots. Those that tuned in to last week's presentation will be able to see that they have some polybelt on here to help bridge that gap and be able to suck in all the balls really quickly. They also have not an intake. So this would be the human player station ramp from 2017. And so the gear just drops down nicely into that. What actuated their arm to deploy the intake? I feel like it was their hopper, because these are all gas struts along here. This is a very, very cool team, very, very cool intake, and their hopper was also quite ridiculous, similar to 971's that year, which is like next level, even for 971.
I will quickly point out that gas struts look very similar to pneumatics, but they are not the same. And so,
Yes.
Yes. Those
On
look
this
like pneumatic
robot,
pistons, but they're not.
there are no tubes coming out of these. They are compressed with, I believe, nitrogen.
Yep.
And so they always want to push out, and you can buy them in different strengths. So I know back at our workshop we have quite a few different gas struts. They can be a little bit expensive, but they're very cool if you have a use for them. Like the deployment just looks so cool. Anyway, we'll jump over to the next one. Maybe. Okay, no, it's good. All right, well, we'll now just go slide by slide and open up the video itself. So this is 3309, the Friarbots. It's a 2019 robot. So you can see here they have. So where 118 had just their claw or their roller claw in 2019, the Friarbots had a extra intake to get that little bit of extra reach and to protect their main scoring mechanism from any damage outside the robot. That's
If
the
they
volume.
took off that intake, they probably could intake anyway as a cutout, like bumper cutout.
Yes, they would definitely be
But
able
yeah.
to.
But yeah, this just gives you the extra reach.
And you can see, I believe this is deployed using pneumatics. You have a piston. Is this a piston? Yeah, it is. The pneumatic piston down the bottom, and it just has a very, very, very limited motion. Very small throw piston. Then we have cones. So again, this is an example of a robot that thought, well, I don't want to make a claw because that's not very touch it, own it. So I'm going to figure out another way to pick these up. So this robot had rollers to pick up the cones, and they were very, very fancy and able to pick up from the human player station with it as well. And angle that bottom part to be able to angle the cone to score on the poles and receive from the human player station and the ground. And it was dual purpose for these inflatable cubes. So once again, rollers and wheels are very, very, very cool and should be your go-to rather than a claw. I guess I don't think we explained why a claw isn't really touch it, own it. So there's the whole, but when you close the claw, you're touching the game piece and now you own it. Okay, yes, that is technically correct. However, you need to be at the game piece and then close the claw. Whereas with any wheels or rolly grabby system, you can drive up to the game piece and it's already yours. You can just drive away. You don't need to close the claw before driving away. And that gives you nice, quick control. Speaking of cubes, this is 179. Oh, speaking of rolly claws, this is the rolly claw of all rolly claws. They have a lot of wheels on here. And so you can see that despite being a claw, they have a bunch of wheels on there to be able to intake the game piece a lot quicker, and they're able to shoot out. So that gives them a massive wide reach when they go to grab a game piece. This probably isn't the most touch it, own it rolly grabber because they do have it very, very wide when they're intaking. But I believe this is their autonomous routine, so it gives them a lot of margin for error. And well, you can see right there that despite their claw and center of their robot being way off picking up the game piece, they hit the inside corner. The wheels are able to bring it over and suck it in to their control, and then they're able to close their claw and take it over to score. And then I believe last but not least, sometimes teams will decide to be polar opposites. So in 2008, 148 decided, hey, I am not going to intake any game pieces. And then in 2018, they decided, hey, I'm going to intake game pieces, but then I'm also going to intake other robots. So this year you got bonus points for having robots above about here. Their bumpers had to be about here. And so 148 decided that it was going to be good to be able to buddy climb with another partner. So that if a team wasn't able to climb, they would be able to bring someone up with them. And you can see that it didn't really matter the size of the robot. They were able to lift them all the way up. So this was then quickly named the Robo Wrangler for good reason. You're able to go around and wrangle whichever robot you choose. And the team was also called the Robo Wranglers. So this doesn't actually intake the bumper of the other robot. It pulls in a piece of Velcro that is attached to the other robot, and then has the plates underneath to be able to support the weight. This was similarly an idea that was done by 1678 in 2020/2021, and by 125, the neutrons in that year as well. We attempted it this year with little success because we didn't know the key secret, which was to have the string running from the opposite side of the robot, not the side you were picking up. Once we figured that out, we tested it in-house and it worked. So disappointing that we couldn't get it during season, but we now know how it works for future seasons. And there we go. That concludes our intake presentation, and we'll open it up for any questions that anyone may have about intakes.
While we're waiting for questions, Luin, did you want to explain the cross-section of the dead axle roller again? I
Yes.
think that was a question that
Am I
people were
sharing
asking.
the screen or the window? If I do this, do we still see? Okay,
You're sharing the window.
do we still see the presentation?
Yeah, that's the presentation there.
Okay, cool.
I might end the recording now that we're in the Q&A section. Before I do that, I'll just pitch our presentation next week. So next week we're hearing from Zach from Project Bucephalus, and I believe also from the unqualified quackers as well. Is that right? Yep. And
That's right.
that's going to be presenting on sensors and control systems. So unqualified quackers was one of the Robot in 3 days teams for the past season, ranked #1 in the world. So if you want to learn some more secrets from the quackers, do tune in next week for that one. And with that, thanks very much for joining us. We will go on with the Q&A and talk about this roller cross section, but I am now going to end the recording. So thanks for joining us, and hope to see you all next week.